Hey, Steven.
Hello.
And hey, Maria.
Hi, everyone. Hello.
So, Steven, how are you?
I'm doing well. How are you?
Good. So, I see a keyboard on the background. Are you a musician?
Not a professional one, but yes, I've been singing my whole life and dabbling on the piano, and so I mostly just use it to accompany myself singing, or me and my wife together singing.
Wow, you should make a video about that. I think it will be really popular.
Yeah, we might be a little shy. Although I think if you search carefully on YouTube, you might find a few things hidden away somewhere.
It must be embarrassing. So that's the whole point.
We enjoy it.
Steven, yeah, I just wanted to say that I'm really thankful to you and your team for the work that you do, because of it, we are able to come to our customers and say that, look, we have made such a great performance improvements for our app, whereas we just retargeted to 5.0. So thanks for that.
You're very welcome. I love to hear that. I mean, that is largely one of the goals. We want people to be able to upgrade as seamlessly as possible and do as much work as we possibly can under the covers to you flip a switch and things just get faster. There are other goals as well, but that's a key one.
So really,
it's great to hear that works.
Today we'll hear a bit about what magic comes into that under the hood.
I hope so, yeah.
So, and I want to remind everyone that we have a Telegram chat. So if you have any questions to Steven about his talk or about performance in general, please join the chat and ask all the questions. Steven knows all the answers to all the performance crazy questions. So, and also I want to remind that we have in our player we have a rate button. So if you want to appreciate the Steven talk and say that you love it, so please rate the talk and write a feedback. It's very important. Yeah, it helps us to improve our talks in the future. So, Steven, what are you going to talk about today?
So, over the last 20 years since .NET was introduced, it's hard to believe it's been 2 decades. Performance has become more and more and more of an important aspect of everything we do, and so I want to take a step back and from a higher level look at the kinds of changes that have gone in, why we've made such changes, why we've been able to make such changes, and the kinds of things that we've done that sort of fundamentally change how we write code, both in the .NET platform and then also for developers writing applications and services that utilize it. And so try and take an hour to take a tour through all of that.
That's really going to be very interesting for all of us.
I hope so. If not, it'll be good feedback to know for the next time I do one of these.
Yes, sounds awesome. So should we start?
Sounds great. All right. Well, thank you for having me, and good evening or good afternoon or good morning, whatever time it might be, wherever you are. My name is Steven Toub. I'm a developer at Microsoft, working primarily on the .NET team. I've been working on .NET for many years, and my primary role right now is sort of overseeing, from a technical quality kind of directional perspective, the libraries that make up, the core libraries that make up .NET. And a key aspect of this is thinking about performance, especially as performance has become more and more and more of a driving factor in everything we do. You look at, I was mentioning .NET's been around for 20 years, and performance has always been something that's been relevant. But if you look at all the things that contribute to the kind of things we do, security has always been and continues to be the topmost concern, right? That's one of the things about managed languages in general. You have a runtime that helps to ensure you're not walking off the end of arrays or countering buffer overflows and other common vulnerabilities that you find when writing native code. But after security, for a long time in .NET's history, usability was sort of of utmost importance, and performance would often take kind of a second seat to that. Now, as we've gone through many iterations of .NET Framework, and now especially with .NET Core, performance ends up really coming just after security as one of the most important things we do. Usability is still critical, and we still think about it in everything we do, but performance now pervades all of our actions. So just as a simple example of this, in .NET Framework 1.0, one of the core collection types was array list. System collections array list. And in addition to not yet having generics, so array list being based on storing objects, which meant you were boxing any value type you would throw into it, the design itself was more focused on usability than on performance. For example, every single method and property on array list is virtual. So adding to an array list is virtual dispatch. Indexing into an array list incurs virtual dispatch. And that then has knock-on effects. For example, in general, we're not able to inline any of those operations, which means you're paying for those virtual dispatch calls in addition to the boxing for every single operation you perform. And something might take multiple nanoseconds versus being less than a nanosecond or something like that, which when you're doing lots and lots and lots of these operations can add up. So then you look at .NET Framework 2.0, not only did we get generics, but when we introduced list of T to take advantage of generics, if you look at the methods on list, none of them are virtual because we recognized that the usability benefits someone might get from being able to derive from that and override this or that method weren't as important as the performance benefits that one got from those being non-virtual operations. And for us being able to optimize the heck out of them, enable fast inlining paths on things like indexers. And then you also see us taking a step further and adding things like list of t.enumerator, which is a public struct that enables for eaching over list of t without allocating. And every release of .NET Framework, you see more and more thought being put into these kinds of performance concerns. And then when we get to .NET Core, the rate at which we introduce these kinds of performance fixes just skyrockets. And that's about changes that we ourselves are making that have to do with performance. That's about changes we're making that have nothing to do with performance. We're still thinking about these from a performance perspective. You also see a large amount of effort being invested in building features almost entirely focused on performance. So for example, there's a type in .NET system.runtime.interop services.unsafe, which exposes a huge number of underlying operations you can't actually express well in C#, and that historically we might have been concerned about exposing because from a usability perspective, it might entice developers that really shouldn't be touching that functionality to go and touch it. But now with .NET Core, we're much more interested in exposing such capabilities for the developers that really need it and being able to utilize the performance improvements that result. The introduction of open source with .NET Core has also been critical in a variety of regards, but in particular, allowing the entire world, the .NET community at large, to really vote with their feet about the kinds of changes they want to see. It used to be with the .NET framework, we were only shipping every few years, and it wasn't open source. And if someone hit a performance bottleneck, even if they knew how to address it, they still had to somehow find a way to channel their feedback to the relevant program manager that worked on .NET in order to sort of register their complaint. And then that feedback had to be prioritized against everything else that the team was going to focus on. And maybe, just maybe, in a couple of years when the next release of .NET Framework shipped, that performance issue might be addressed in one way, shape, or form. Now with .NET Core, same situation. A developer hits a performance issue. They go and they figure out what it is. They submit a PR to .NET Runtime. We review the change, and hopefully within a few days, sometimes longer, but it's generally within a few days, we've reviewed it. We've worked back and forth with the developer. We've merged the fixed. It shows up the next day in the nightly builds. It shows up the next month in the previews that we're shipping, and the next release that we ship within a year contains that performance improvement. And this allows us to scale and make .NET really for everyone, where we're not just bottlenecked by the tens of developers on the .NET team and more the thousands upon thousands of developers around the world that are using .NET. All of this has resulted in monumental improvements in .NET Core in particular when it comes to performance. And back in several years back, I guess about 4 or 5 years ago when we shipped .NET Core 2.0, I sort of realized we were doing all this work in performance and we weren't really talking about it. So I went through and I sort of summarized at a high level a bunch of the kinds of changes that were going into the release. Wrote a fairly lengthy blog post about it, and it got good reception. So then when we shipped .NET Core 2.1, which although it's a dot release, a minor release, it actually was pretty monumental. It really probably should have been a major release. And I did it again. I wrote a blog post summarizing all the improvements, and it ended up being even longer than the first. And then again for .NET Core 3.0, it ended up being even longer than the previous. And again for .NET 5. And I haven't yet started on it, but I will probably soon for .NET 6, because every release, I think to myself, wow, that was a huge amount of change. How could we possibly top that? What am I possibly going to have to write about next time? And then over the course of the next few months, and I see these changes coming in and improvements coming in to the point where now for .NET 6, we've actually, we're still only about halfway through building .NET 6, and there have already been more performance-focused changes that have gone into .NET 6 than there were in all of .NET 5. So it's pretty exciting. And if you are interested in these improvements, I'm assuming these slides will be distributed and you'll be able to just click the links. But if not, if you just search for these titles, you should find them in Google or Bing or your favorite search engine. The impact of these changes that we make generally shows up in one of two forms. One is what Maria was alluding to earlier. We really want people to be able to flip a switch, change their target framework, upgrade to the new release, and things just get better without them having to change any code. Like, that's our ideal. And so a lot of the improvements you see going into the release are focused on that. How do we take the existing APIs and just make them better? On top of that, we do want people to be able to utilize new functionality. And a lot of the new functionality we end up adding, some of it is functional, some of it is taking patterns that people are trying to do, or new collection types that people want, and implementing those, and doing so in a highly efficient manner. But a lot of the work we end up doing is also exposing new APIs that enable developers to get better performance if they're willing to write a little bit of code to utilize that new functionality. And then when we do that, we also then try and utilize that same functionality in our existing APIs to better serve the folks that just want to be able to flip a switch and upgrade and things get better. And so, if you kind of look at the PRs that come into .NET Runtime and you see someone implementing a new API and you see me commenting on that PR, one of the things you'll often see me ask is, where else should we be using this throughout .NET Runtime? Because .NET Runtime is millions of lines of code. If we're adding a new API, there's a really, really good chance that we should be and could be using that somewhere to improve the performance of something else. And if we can't, that's potentially an indication that the thing that we just developed, that was just implemented, may not have the right design. Because if we can't use it ourselves, either it's super niche or it's potentially designed incorrectly. So these are the kinds of things that we've been thinking about as we think about performance improvements going into .NET. There are a variety of interesting aspects that have impacted our ability to make performance improvements in .NET that folks may not think about, and so I wanted to highlight a few of those. One of the most interesting for me, in large part because you don't generally think about this as part of performance, and it is arguably the number one thing that has caused us to be able to improve performance in .NET, is how we distribute .NET itself. So .NET Framework is distributed as part of Windows, right? It's Windows only, whereas .NET Core is cross-platform. And it is part of Windows, just updated in place. That means when you get a new version of .NET Framework, you install it onto your machine, you patch it, whatever, you are overwriting the existing one you already had. And that means anytime we do anything in .NET Framework, and that gets deployed to someone's machine, it has the potential to break any app on any Windows machine anywhere in the world. And the numbers are quite large as to how many that is, to the point where pretty much any change we make, given the numbers involved, can and will break someone, even if that change is 100% purely correct. We've had changes we've made that were entirely about making something faster. By any measure, it was 100% correct. No bugs. It was doing exactly what it was supposed to do, didn't change functionality at all. It just made something faster. And yet we still broke someone we still broke someone because we made something faster and it exposed a latent race condition in someone's application such that they never ever hit it before. But when they deployed on the new version of .NET, on the new version of .NET Framework, we made a certain aspect of their code faster, just fast enough to start exposing that race condition. And now all of a sudden, deploying the new version of .NET Framework broke the rap. Microsoft broke the rap, right? That becomes the meme. And this makes it very challenging for us to even make performance improvements, never mind other improvements. We've had some pretty visible breaks in the past. In 2008, we deployed a change around March or April that ended up breaking printing in TurboTax. Now, if any of you are in the United States, for those of you who aren't in the United States, you should know that every year, come April 15th, our United States taxes are due to the United States Internal Revenue Service. And TurboTax is used by millions upon millions of Americans to submit their tax returns to the IRS. You do not want to break TurboTax in tax season. And yet we did it not only once in 2008, we did it twice again in 2012, to the point where we basically now say, unless it's something really critical, we're just not going to ship updates to .NET Framework in tax season because we're so concerned about the impact of that. So all of this has basically prevented us from doing the kinds of improvements in .NET Framework that we would like to do. We are going to maintain .NET Framework for a very, very, very long time, especially from a security perspective. But we've really largely stopped making minor tweaks here and there to incrementally improve the performance of something. And if you look at .NET Core, a lot of the improvements we've been able to make are an incremental improvement here, an incremental improvement there that add up. Well, why are we able to do this in .NET Core? Well, largely it's because of the distribution vehicle. So first, .NET Core ends up being installed side by side. I can have .NET Core 2.0 on the box, and .NET Core 2.1, and .NET Core 3.0, and 3.1, and .NET 5, and a nightly build of .NET 6. I can have all of those on my machine at the same time, and different applications can be targeting different versions. Not only that, I can actually build an application that includes everything that's necessary from .NET Core as part of it, entirely self-contained, not dependent on anything else on the box, such that if we did make a patch that broke something, that application would be contained away and isolated from that break. Not only that, but when you ship such a self-contained version of .NET, you can actually trim it down. In fact, we're investing pretty heavily in this trimming support in .NET 6, largely in support of application models like Blazor with WebAssembly, where you can deploy your entire application down to the browser. And even though .NET Core might be, say, 50 megabytes, you can build your application such that it takes up, say, 1.5 megabytes at the end of the day, entire framework and application code included. All of this distribution has then enabled us to have a much, much higher risk tolerance. Breaking changes for us are obviously still a big deal, and we document all the breaking changes we know about. Here's a link to the one you can search for this, breaking changes in .NET 5, and you'll see the list of changes we knowingly made because we wanted to fix a bug or improve the performance of something, and it was worth taking a minor behavioral change to do so. But we're able to move a whole lot faster. We're able to churn code a whole lot faster because we have this higher level for risk. And this includes both these incremental improvements as well as huge overhauls of entire systems where we've decided it's time to, we can do everything by better if we just start from scratch and rewrite something. And this also allows us to accept a significant number of contributions from the community at large, whether it's from the .NET team itself, or other folks at Microsoft, or others that have nothing to do with Microsoft but are just interested in improving .NET. So distribution vehicle has been a critical aspect of our performance improvements in .NET, as has open source. I alluded to this earlier, but if you look at the blog post that I mentioned around .NET 5, I summarized in it around 250 PRs that went in that were pretty much focused entirely on improving the performance of something in .NET. Now, the actual number, I wrote this post last July, and we didn't ship until November. And between that time, there were more improvements that came in. So it probably ended up being closer to around 300 PRs. But about 20% of them, a little more than 20% of them, were from people outside of Microsoft. These are improvements where people were able to say, you know what, this isn't something that I see Microsoft focusing on. This isn't a change that is on the primary goals for the .NET team. But I found something that's important to me in my application, and I'm going to go and I'm going to fix it. I'm going to improve it. And so around 50 of these 250 PRs ended up being people from the broader .NET community making performance improvements to .NET itself, because it helped to forward their own goals. And I mentioned this already, but in .NET 6, we've already seen more than this, and we're still only about halfway through the release. So that's pretty encouraging for what the release is going to end up look like, and also a little bit daunting for me in terms of writing the next blog post that I plan to do probably in a few months. And these changes that you see run the gamut for what they impact. So, for example, we had a long-standing issue about the amount of time that we were spending in the prologue of methods. When you enter a method, the JIT needs to emit some code to zero out some of the space in the stack frame, so that when the GC kicks in and looks at the stack frame, it doesn't see garbage. It needs to either see valid addresses and references or zeros in those references. And so the prologue of the method ends up having to zero out some of that state. And some of the coding patterns that we've been employing more and more in .NET, we'll get to this a little bit later, have increased the number of references, especially in temporaries, that show up in stack frames, which means we spend more and more time zeroing. So one of our more frequent external contributors came in and took advantage of basically vectorization, vector instructions, to speed up that zeroing. And this resulted in some methods being 20% faster, 15, 20% faster, and impacting a huge amount of functionality across both the core libraries and applications by this change that just impacted the prologue of methods. Other times, these changes end up being more niche. For example, someone was really interested, was using color, the system drawing color type a lot, and wanted to significantly improve the performance of some of the color space conversions. So they submitted a PR for that, and we happily accepted it. And then other times it's more experimental. In this case, it was the Bing team at Microsoft was interested in trying out some support with large pages from the operating system. And they added support to the runtime. It's available for everyone under an experimental switch, which you can go find documented in the GC documentation. And they added this functionality so that they could explore it. We love all of these kinds of changes, and it's significantly moved the platform forward. The ability for not only folks on the .NET team, but others at Microsoft and others around the world to do so. Now, when it comes to what kinds of changes we want to accept, or we encourage folks to submit, or we work on ourselves, we have become extremely driven by data. One key piece of data that we focus on is micro benchmarks. So we have, for the most part, standardized on benchmark.net. If you haven't used benchmark.net, I highly encourage you to try it out. It's simple to use. You just use .net add package benchmark.net, goes up to NuGet, grabs the package, modifies your CS proj appropriately, such that you can then start writing code. And so, for example, you can have your entire program be something like this, which says my main method is basically saying, hey, benchmark.net, find all of the benchmarks in my whole assembly, and then run them. And when it runs them, it can take a little bit of time, but it runs them over and over and over again, and then does a variety of statistical analysis to find exactly how long this benchmark is actually taking. You can also see that I've attributed my program with a memory diagnoser. Benchmark.net includes these additional diagnosers that give you additional data on things other than just CPU speed or throughput. In this case, I'm asking for it to collect data from the GC. So how much did I allocate? How many Gen 0, Gen 1, Gen 2 GCs occurred, et cetera. And my one benchmark in this case is just seeing how fast we can produce the string representation of an int 32. You run this, it spews out a bunch of data to the console, and then eventually you end up with a table, which I've copied and pasted into PowerPoint, which I'll show in a moment. I run this using the .NET run. So -c release means run this in release builds. -f net48 means build against the .NET Framework 4.8 surface area, because I'm actually going to test this on a bunch of different runtimes, and I want to use the oldest one to make sure that I'm only using surface area that exists everywhere. The filtered ** says include everything. And then I want it to run on .NET Framework 4.8. I want to run it on .NET Core 2.1, on .NET Core 3.1, and on .NET 5. Again, I have all these on my box at the same time because I can have any number of .NET Cores on my box at the same time. I run it, and it produces results something like this in PowerPoint form. And you can see on .NET Framework 4.0, this simple operation of doing int32.2 string with this 1, 2, 3, 4, 5 value was taking about 48 nanoseconds and was allocating about 40 bytes. And by the time we get to .NET Core 2.1, we've made enough incremental improvements here that we've basically more than halved the time that it takes to do this, going from 48 nanoseconds to 22 nanoseconds. .NET Core 3.1 comes along. We've shaved off another few percentage points. We've also reduced how much allocation is involved. And then .NET 5 comes along, and we've again halved how long it takes, such that it's about 4 to 5x faster than it was on .NET Framework 4.8. And you can see these kinds of changes. This is one small example. These kinds of changes have happened en masse throughout, impacting pretty much any piece of functionality you can think of. So micro benchmarks are one thing that we focus on, and we use this not only for performance-focused changes, but even changes that aren't focused on performance. Anytime anyone submits any change that we think might possibly impact the performance of something, we ask for micro benchmarks on that thing. We also have the .NET Performance repo, which contains a myriad of benchmarks, which we run on a very frequent schedule to be able to catch unexpected regressions. Another thing we focus on is not just micro benchmarks, but also industry benchmarks. And one of the key set of industry benchmarks we've been looking at is Tech Empower. Tech Empower is a consulting company that, in addition to their consulting work, also has this set of benchmarks that they encourage submissions to from various frameworks and languages and whatnot. And one of those is this plain text benchmark, which really measures the raw overhead of a web server in doing a particularly very small request response kind of scenario. And you can see that ASP.NET Core, because of all the performance improvements we've done over the years, is right up there at the very top of the pack. And depending on how the winds are blowing, it ends up being number 1 or number 2, because we're at this point, everything at the top of the pack is limited basically by network bandwidth. But there are other benchmarks that are part of Tech Empower. One of the ones that we focused on in .NET 5 was improving our standing on the Fortunes benchmark, which is really a database access benchmark. Request comes into a web server, the web server makes a request to a database, response comes back, response goes back to the client. And you can see this is all running on Linux. We were around position number 24 or 26, depending on the configuration that we were using, getting about 280,000 requests per second on this benchmark. And for .NET 5, you basically upgrade to .NET 5, and now instead of being position 24, we're position number 9, doing about 400,000 requests per second. So about 30-ish% faster than in the previous release, 40% faster than the previous release. Which is pretty exciting. We also focus on kind of raw dollars. We have access to data from, say, our own services at Microsoft and Azure, how many cores a particular piece of functionality is taking up. And I will peruse this data every now and then, looking for functions, looking for types that are taking up a significant number of cores. And my threshold is sort of, if I see something taking thousands of cores per day, that's something that I probably want to go and look at. So as an example of that, this isn't an exact regex that comes from these services, but it's one I found on the web for parsing email addresses. And in .NET 5, we noticed that we were spending a lot of cores and dollars running regular expressions. And so we invested pretty significantly in .NET 5 in improving the performance of the regex engine, which had largely gone untouched for over a decade. Closer to 15 years probably. And you can see the impact of this when I run this benchmark, which is just seeing whether someone at example.org is an email, if it matches this regex. You can see on .NET Framework 4.8, this was taking about 470 nanoseconds. There had been some mild improvements that had gone into .NET Core 3.1, resulting in it being about 20% faster. But then in .NET 5, that dropped to about 150 nanoseconds. So 3 to 4x faster than what it had been in .NET Framework 4.8, which if you're spending thousands of cores, makes a significant difference in how much it's costing for services to run. Another example in my thousands of cores club is compression. So this benchmark is downloading. I can't remember exactly what I grabbed. I think this is the complete works of Mark Twain as a text file from the Gutenberg project. Downloading it, compressing it, and then over decompressing it to see how long it takes me to asynchronously decompress this from the input stream to just the null dumping ground. And you can see on .NET Framework 4.8, this was well, actually, apparently I forgot to include the mean values here. But for .NET 5, it got about 20% faster, but it also ended up allocating about 350K less per iteration. This 20% faster is also a little bit misleading in that, for the most part, we haven't been porting performance fixes back from .NET Core to .NET Framework. I can think of I could probably count on one or two hands the number of times we've done this, but we have in a few specific cases for really impactful changes. And this is actually one of them. For .NET Framework 4.8, we ported back some improvements that had been made to Deflate Stream because they were decreasing the cost of such decompression by about 3x. So if you were to actually compare .NET 5 against a previous release of .NET Framework, say .NET Framework 4.7, it would be about 3 to 4x faster. And it's only because we took these perf improvements that we had in .NET Core and cherry-picked them back into .NET Framework that we were able to see this relatively small increase with .NET 5. Another example, the two that I just showed, regex and compression, those are sort of meatier things, right? But oftentimes it's the small operations that are done over and over and over and over that actually contribute to this. So take dictionary, for example. This benchmark is just doing a bunch of try get values on a dictionary using ordinal ignore case, which is pretty common, especially in web scenarios. And even for something as small as just looking something up in a dictionary, you can see that the kinds of improvements we've made from release to release have made a measurable difference. So .NET Framework 4.8, this operation was taking about 58 nanoseconds for doing approximately 1,000 lookups in the dictionary. That was almost halved for .NET Core 3.1, and then that was again almost halved for .NET 5, such that .NET 5 ends up being about 70% faster than the same operation was on .NET Framework 4.8. And if you're doing lots and lots and lots of dictionary lookups, this adds up. We also focus on things that show up in very commonly in web scenarios. So I grabbed some text off the .NET marketing website, and in a website, you're very frequently doing encoding conversions, going from UTF-16 to UTF-8 and back, or from UTF-8 to UTF-16 and whatever. So this is round tripping. I'm taking a string, I'm getting the UTF-8 bytes for it, and then I am converting that back to the UTF-16 string. And again, .NET Framework 4.8, you can see this taking 190 nanoseconds, and .NET 5.0 being around 60% faster at 80 nanoseconds. Again, because of all these improvements that have gone into various encodings. This doesn't just apply to UTF-8. This, for example, applies to encoding Latin 1, which is also used in a lot of web-related things like HTTP. So how do we accomplish these improvements? Like we've seen some examples, and there are a variety of ways that these improvements come about. In some cases, it's complete rewrites. So Concurrent Queue, for example. Concurrent Queue was introduced in .NET Framework 4.0, so circa 2010. And it did its job. It was good. But we recognized that for the kinds of things we wanted to use Concurrent Queue for, it just wasn't as good as it could be, especially with regards to allocation, which then in turn impacted the number of GCs that were happening, which in turn impacted the overall throughput, as well as pause durations, where the whole app would just pause while waiting for the GC to do its job. So in .NET Core 2.1, we rewrote this thing entirely from scratch. I we probably saved a few lines of code, but for the most part, it was from the ground up. And the focus here was really on reducing the synchronization between producers writing into the queue and consumers taking out of the queue. As well as driving down the memory use. And we did that in particular where when you get to steady state with concurrent queue, where its internal data structures have grown large enough to handle sort of the steady state throughput that's required for a given usage, it ends up being amortized allocation free, which you can see in a benchmark where we've got a concurrent queue here. And I'm just spinning up two tasks. They wait for each other so that they're both ready to go. And then one of them enqueues a million integers, and the other one loops until it's able to dequeue all of those million integers. And if we look at the results for this on .NET Framework 4.8, not only can you see this going from 45 milliseconds to about 12 milliseconds, so about 4x faster, you can see the allocation has gone from about 8.5 megabytes to basically nothing. And this is in particularly very valuable because we were now able to then use concurrent queue as the thread pool's main queue. So now when you queue work into the thread pool, it's using this steady state amortized allocation free data structure that is concurrent queue, getting the throughput benefits. And it's one of these examples where we improved the core data structure and made everyone else faster, and we were able to use it ourselves to make other areas of the system faster as well. So sometimes we achieve this with complete rewrites. Sometimes we achieve this by fundamentally changing the algorithmic complexity of certain operations. So for example, link. Link is basically the enumerable class is really useful. We talked about usability earlier. Link is all about usability, being able to take one enumerable and do various transformations on it to get other enumerables or arrays or lists or whatever. Its design is sort of inherently not focused on performance. And it's really good for if you don't care about the absolute fastest possible throughput, but you want to succinctly express your concepts. Link is great for that. Even so, we still, because of that, lots and lots of code ends up using Link. And so we still want to make Link as fast as we possibly can, given the design constraints involved. And so we've spent, especially folks external to the .NET team, have spent a lot of time over the last few .NET Core releases improving the performance of Link. One of the things we've done here is enable various Link operators to pass data sort of through a side channel, essentially, from one operator to another. And this allows information from earlier in the query to impact optimizations performed. So take this this example here. I've got an input array. I'm doing an order by on it. I'm then skipping the lowest 10 values. I'm taking one, and I'm not sure why I added the dot sum there, but I've added dot sum. It would make more sense if I said take two, I guess. In previous releases in .NET Framework, when you did that order by and it was lazily evaluated, it would do a full sort. And then after that full sort, you would skip the first 10 values, and then you would take one of them, and you would compute the sum. But we can pass information down through all these operators, so that by we actually do it to lazily compute it, we can see you don't actually need a full sort. What you really need is the 11th item from the bottom. And as a result, we don't have to do a full sort. We don't even have to do a partial sort. We can do a partial quick select to only sort the portions of the output that are necessary in order to get to that element that we need. And you can see the impact of this completely changing the algorithmic complexity on a data source that's 10 million elements, going from about almost 4 seconds to 200 milliseconds. And these kinds of changes have pervaded a bunch of the link operators, both reducing overheads and just changing how much time we spend computing for a particular operation, just not doing unnecessary work. So sometimes it's these complete rewrites. Sometimes you're focused on a particular data structure. Sometimes it's changing algorithmic complexity. Sometimes it's just fundamentally changing how we write our code and introducing new concepts that we can then utilize that end up, again, pervading everything that we do and everything that folks do on top of us. And one of the I think arguably the most impactful cases of this is span. So span and read-only span were introduced in .NET Core 2.1. Fundamentally, it's just a little struct that contains two things. It contains a managed pointer, and it contains a length. Now, the syntax that I've written on the screen, you can't actually compile, but logically, this is what it is. It is a ref struct, which just means it contains it contains a reference. And the ref here is the same kind of ref you would see if you were passing a value by ref to a method. It's just that we're able to put one inside of this structure. Now, in order to actually express this in the runtime, because this language feature for the ref field doesn't yet exist, we have a special mechanism for doing it that the JIT recognizes. But fundamentally, this is what it is. And this span allows us to provide a zero allocation representation of any kind of contiguous memory. So we can take a string, a system.string, and view it as a read-only span of char. Or we can take an array of person and treat it as a span of person. Or we can stack allocate some bytes and treat that as a span of byte. And because the compiler knows that span is safe and it's bounds checked and you get all sort of the correctness guarantees that you get from arrays, you can write that line of code, span of byte s equals stack alloc byte, without having to tell the C# compiler you want to be able to use unsafe code, because fundamentally it is not unsafe. If you are using unsafe code and you already have a pointer, great, you can wrap a span around it, and now you can get bounds checking and all that kind of support with your native pointer. And you can do all of that. The really neat thing about this is you can write reusable routines that are now able to operate over spans or arrays or stack allocated data or a pointer to native data you got from somewhere else. So you only have to write your routine once, and you can use all of these input sources. Not only that, you can do really interesting transforms. You can index into this just like you can with an array, and it's fully bounds checked just like it is with array. In fact, there are certain optimizations that show up here especially for assignments into span that actually enable it to be faster than it is with arrays. You can slice these things either using the slice method or using the C# support for the range syntax. You can reinterpret these. You can take a span of, say, integers and then pass it to a routine that operates over a span of bytes. And it ends up being effectively a zero-cost transformation, a little bit of multiplication to do that transform. And then on top of that, we end up having tons of methods throughout the framework, and more every release, that end up operating on these spans. And this has enabled us to fundamentally change how we write our code. Every release, more and more code is transformed from being array-based or string-based or pointer-based to being span-based. This provides us with some significant performance benefits as well as safety benefits. We're now able to take code where we had been using pointers for performance and significantly reduce our vulnerable surface area by transforming most of that to use spans and then only using pointers still in the fastest, hottest loops where we really need the utmost in performance. But it's also enabled the JIT to get in on the game, and the JIT, every release, ends up getting more and more optimizations that are focused on spans, finding more and more patterns where it can eliminate bounds checks. Even the C# compiler has gotten in on the game, and there are patterns you can write now using spans. For example, you can have a property that a static property that is typed to return, say, a read-only span of byte, and that is written to say new byte with only constants filling in that byte array. And the C# compiler can say, interesting, I see you're creating a byte array, but it's only filled with constants, so there's no variable data, and you're storing it into a span, a read-only span, which means no one can write to this and no one can extract out the underlying array, which means no one can really know that there was an array backing this at all. So rather than emitting code that actually allocates a byte array, it just blits that data into the binary, and when you access that property, it returns you a span that's just wrapping the pointer to the data in the binary and the length. So it becomes less overhead and way faster less allocation. Plus, when the JIT then inlines it, it gets information about how long that thing was. And so the JIT can do additional optimizations that treat the length of that span as a const that it can then propagate through the remainder of this method. So you have these knock-on effects after knock-on effects after knock-on effects that allow using spans to significantly improve both the safety and performance of your applications. So what does that look like? So this is just a simple example. Let's say I wanted to concatenate. I wanted to say hello and then a name that was in quotes. So in this case, I'm saying hello, Stephen. And I want to strip off the quotes. So I want it to be hello, Stephen without the quotes. So previously, if I was writing this on .NET Framework, I might have done string.concat, hello as a string, and then take the input string and use substring to strip off the first and last quote. Now, I can run that on both .NET Framework and .NET 5, and you can see it was taking about 25 nanoseconds on .NET Framework, and we made some performance improvements even here for .NET 5, so it's about 20% faster than it was on .NET Framework. But then you can, let's say we introduce spans. So now I can rewrite this. I can create some stack space for the span to write into. I can copy the hello string into that span. Then I can slice the input string, so I'm not allocating to get just the Stephen portion without the quotes, and copy that to the relevant position of my sliced destination span. And then I can slice just the portion of the resulting span that I care about, call toString on it. So more code, a little bit more complicated, but that gets me down to not only 18 nanoseconds instead of 25 or 22, but about half the allocation. Okay, but then we say, well, this is a pretty common pattern. People are going to want to be able to concatenate these spans like this. So we introduce a new overload of string.concat that takes spans instead of strings. Now, strings in .NET Core are implicitly convertible to spans, so I can just pass, even though this takes 2 read-only span of char arguments, I can still pass my hello string directly, and then I can just pass my quoted name sliced span directly in. And this ends up being even faster at 12 nanoseconds, a whole lot less code to write. And this is why you see these span overloads being introduced across the framework. I could have written my say hello to be just as efficient, but it would have it would have taken a little bit more code to do so. Obviously, this ends up showing up in other places beyond just strings. And as I mentioned, we've been investing a whole lot of effort in moving lots of code that was using pointers or arrays or strings to be span-based. There are a variety of reasons for this, but one of the most interesting is in that we've actually been doing something that might be counterintuitive to folks. And that is, you talk to most people and they will say, oh yeah, if you really want the utmost in performance, use native code, use C or C++. But in reality, we've actually been porting a huge amount of code that was in our runtime as C or C++ and actually moving it to be C# exactly for performance. Well, not just for performance. There are a variety of other reasons we've been doing it. One of the main reasons we've been doing it is to be able to better share code between our runtimes. We have actually multiple runtimes. Most of the things that I talk about are on Core CLR, but Mono is also part of .NET Core. We have another runtime that is focused on AOT, ahead of time compilation, and we want to be able to share as much code as possible between these runtimes. Now, all the libraries above corelib are all basically shared as is between these. And even large parts of corelib are shared between all these. At this point, it's about, I think, 96, 97% of all the code in corelib is identical between the actual runtime that's being used. But then there was all the code in each runtime, and anything that was in there was really hard to share. And so we've been moving some of that code out. Now, as we move it out, we are able to not only better share it between runtimes, but we're able to rewrite it using things like span to get the safety benefits that come from having this code be in managed bounds check code versus the native unbounds checked security vulnerable potentially code that was in the runtime. And interestingly, this also comes with some noticeable performance benefits. So we, for example, took all the sorting code that was in the runtime. It was like the sorting code that you hit when you're trying to do really efficient sorting of primitive types, integers, doubles, longs, etc. We moved that all into managed. Once it was in managed, we used span. Once it was using span, we exposed these APIs publicly. So they're now public sort APIs that operate on spans, which means you can use the exact same sorting routine to sort data on your stack or native data or arrays or whatever. We then also took those APIs and used them elsewhere. So now when you call array.sort under the covers, that's actually casting the array to a span and using the span-based sorting. Or when you use links order by under the covers, you're actually calling into the span-based sorting APIs. But it's actually had some measurable performance benefits. So especially for smaller arrays, smaller inputs. So here I've got a reverse sorted array, which is sort of the worst case generally for something like quicksort. And I'm just sorting it over and over and over again. And you can see that on .NET Framework 4.8, this was taking about 100 nanoseconds. On .NET Core 3.1, we had improved that by about 15% to 85 nanoseconds. And then by .NET 5, where we actually moved all this logic into managed code, it was actually twice as fast as what it had been when it was, or almost twice as fast as what it happened when it was in native. So a lot of this comes from just, we've tried to make the cost of calling from managed code into native code as small as possible. In fact, we play some pretty significant tricks in the runtime to be able to do so. We'll talk more about that in a moment. For these small operations, the overhead of that transition actually contributes a pretty sizable amount. There's another thing that this ended up helping with, and that's to do with GC pause time. So I mentioned that just a minute ago that we play these tricks when we make these calls from managed code and core lib into the runtime. We have these things called F calls. And basically, we're able to transition into the runtime in a way that prevents the garbage collector from being as aggressive as we would like it to be about pausing threads. We do this only for really fast operations, and generally we then make those operations sort of manually synchronize with the garbage collector to give the garbage collector the opportunity to pause that thread when it needs to. But sometimes this always doesn't work out as we would like. So for example, here I have a little application. It's spinning up a background thread that is repeatedly calling array.sort in a loop over and over. And this array is always sorted. So array.sort is basically doing no work. Just array sort. Then on the primary thread, I, in a loop, force a full collection and then sleep for about 15 milliseconds. And then I time how long that whole thing took. And I do that over and over. So I'm sleeping 10 times for 15 milliseconds, or it ends up being closer to 16 milliseconds. So this is going to take about 160 milliseconds plus 10 GC collects. So let's round up to around 200 milliseconds as our hand wavy estimate for what we think this is going to cost. When I run this on .NET Core 3.1, which is also approximately the same as we would see on .NET Framework, we end up with numbers that look very different from what we estimated. This isn't 200 milliseconds. This is 3 seconds, 4 seconds, 5 seconds to time this loop. And the reason for that is the garbage collector is having a very difficult time as part of that GC collect, suspending that thread that is just in a tight loop making these F calls into the runtime. And it's constantly trying, can I pause you now? Can I pause you now? Can I pause you now? And only when it's able to is the GC collect able to then do its job and return and allow us to proceed. On .NET 5, where we moved that sorting code into the runtime, you can see we're much closer to the hand wavy 200 milliseconds that we estimated, because with all that code in managed code, the GC is able to do its job a whole lot better. So if you look at the kinds of changes that we were making in .NET Core 3.1 and .NET 5, a lot of them involved moving huge swaths of functionality, pretty much everything on array. Whether it's array reverse or index of or sorting, this is all now in managed code. Which is pretty cool. There's another interesting performance aspect of this as well, which I didn't talk to, but ties in with the community aspect that we looked at earlier. And that is developers in .NET Runtime, working in .NET Runtime, are generally happier working in C# code than they are working in native C and C++ code. And that means that we end up seeing many more PRs to incrementally improve the performance of things in C# than if they were in C, which then means that we end up seeing more time investment in making these kinds of incremental improvements. At the same time, we're also happier to accept them because unless we explicitly see unsafe things in the code, we know that there's some additional amount of security being applied to the change than if it had been made in native code, where there is no bounds checking. We have to be much more scrutinizing about things like buffer overflows. And so it takes us longer to review. And so we're able to churn less fast. And we're just not able to see the benefits come in as quickly as we would like. So moving all this stuff into C# has had a multitude of benefits. And a lot of it is thanks to SPAN. Another area that's sort of changed how we write code, both in the core libraries and above, is async. And another example where we completely wrote support for something was with async. So in .NET Core 2.1, we completely rewrote the infrastructure in the runtime for supporting async methods. And the effect of this, especially on micro benchmarks, is pretty obvious. So here's a little benchmark that is setting some state into an async local, because that's pretty common. And then 1,000 times it's awaiting this yield once method, which itself is going to call await task.yield. So a simple little example. We can see some interesting things from this. First, in .NET Framework 4.8, this operation was taking about 2 milliseconds, whereas in .NET Core 2.1, it was taking about 920 microseconds. That improved by another 10% or so for .NET Core 3.1, and another few percent for .NET 5. But the interesting thing to notice is the allocation. This rewrite significantly reduced the amount of allocation required for async methods when they end up yielding. So to the tune of about 5x in this case. So pretty monumental improvements. Now, obviously, there still is some allocation. We can see what that is. So in .NET Framework 4.8, you can see all this stuff, right? We're allocating multiple execution contexts. That's in support of the async local. There are these actions and move next runners. The logical call context is part of the execution context. There are these work items that we're queuing into the thread pool. A lot of stuff. .NET 5, there's one allocation. That is this async state machine box, which is an internal type that actually derives from task of T and carries with it everything it needs to support this async method. And that's where this 112K comes from. We're allocating 1,000 of these objects as part of this benchmark for the 1,000 loops. Each one is about 112 bytes, and that's where we end up with 112K. But that's still an allocation. Wouldn't it be nice if we could get rid of even that task? So we introduced value task. Value task is a struct that in its initial incarnation basically was a discriminated union between a T and a task of T. So it's a struct that could contain either a T or a task of T. And this was great for asynchronous methods that actually completed synchronously, which is pretty common. Take something like a stream, where you call read async. And the first time you call read async, it has to do I/O to populate its buffer to fill up a bunch of stuff. But then X number of times after that you call read async, it doesn't have to do I/O. It's just pulling state from the buffer, which can all complete synchronously. But even in that case, we were having to allocate a task of T, a task of int, in order to return the results to the caller. Now, we were able to play some tricks in certain cases for small values of T or for multiple calls that ended up returning the exact same value. We were able to try and amortize that task allocation. But in general, every call resulted in a task. So value task of T allowed us for the synchronous case to just return a value task of T that was wrapping a T rather than one that was wrapping a task of T. But then in .NET Core 2.1, we took this a step further and introduced some interfaces that value task could also wrap. So it could basically be either a T or a task of T or an iValue task source of T, which allowed someone to plug in their own implementation behind this and do fun things with that, like pooling. Such that it became possible to avoid that allocation even for the asynchronous case. And we've then taken advantage of this ourselves. In every release of .NET 5, we've added more support, and .NET 6 is going to see even more for this. But we can take this simple example. I'm just, in my setup here, I'm creating 2 connected sockets. Then I have a loop that does a receive on one of the sockets. Now, there's no data pending, so it's always going to be asynchronous. Then on the other socket, I send it some data, and then I wait for that data to propagate so it can be received. I just need a drink. And we can see the impact that that these asynchronous improvements have had. In .NET Framework 4.8, this was taking about 35 milliseconds and was allocating about 333K for this operation, for these 1,000 calls. But in .NET Core 2.1, not only did we rewrite the async infrastructure, but we also added new overloads to socket for send async and receive async that rather than returning task of T, return value task of T. And socket is able to maintain a reusable I-value task source such that every call it can just return that same object under the covers, and we end up with no additional allocation beyond the initial one for any number of operations we perform. And that's how you can see in .NET Core 2.1 that 333 KB dropping to nothing. In addition to all the other incremental performance we've made in sockets and async in every release, such that by the time we get to .NET 5, you see what was 35 milliseconds and 333K being only 18 milliseconds and nothing allocated. Another example is array pool. We now use this pervasively everywhere. Lots of operations would end up allocating little arrays for things or big arrays for things. And over time, we've been transitioning more and more from those being just new allocations to being ones from this shared array pool. So this is almost a copy and paste from some code in the base stream class in support of stream.copy2async. And you can see, in previous releases of .NET Framework, this would allocate something around an 80K byte buffer by default as part of this copy2async. Now, instead of allocating it, we just rent one from the buffer, we use it. Sorry, we rent one from the pool, we use it, and then we return it back to the pool when we're done. And this has significantly decreased, especially Gen 2 garbage collections and Gen 1 garbage collections, because a lot of times these arrays, especially with asynchronous operations, end up surviving some number of garbage collections. And this has allowed us to avoid significant numbers of garbage collections, and as a result, significantly improving throughput. One more example, hardware intrinsics. Now, this is some pretty low-level, deep stuff, but we end up using these hardware intrinsics and vectorization throughout key functionality in the framework. This is basically support for taking advantage of additional instruction sets that the hardware has to offer, whether it's SSE2 or AVX2 or advanced SIMD on ARM64. Whatever it is, there are these instructions that the processor supports that we've now exposed C# or .NET APIs for that you can call to get access to those raw instructions. And we now use this as well as the sort of higher level vector types in span and string and bit array and encoding across the gamut. So just a little example of this, some Shakespeare, and I'm just looking to see if this text contains the word shines, which it does at the end. And this is taking advantage of contains, which is vectorized using this functionality. You can see that on .NET Framework, this operation was taking about 41 nanoseconds. For .NET Core, it was vectorized. It took about .NET Core 2.1, it took about 10 nanoseconds. We then started taking more and more advantage of more of these intrinsics, doing things that couldn't be done with the vector type itself. And you see that drop into 7 nanoseconds and 6 nanoseconds, to the point where now .NET 5 is basically 90% faster, 85% faster than the .NET Framework was. You can also take advantage of these directly in your own code, but it's another case where we've introduced these new APIs, which you can use, but we're then using everywhere we can internally, such that when you just upgrade to the next version, all of this stuff just works better. So that was a lot of stuff, and obviously there's a whole lot that I haven't talked about. But for that, I would encourage folks to go and read the blog posts that I talked about. There are hundreds upon hundreds upon hundreds of PRs and explanations into what those PRs did in those blog posts focused on .NET Core 2.0, 2.1, 3.0, 5.0, et cetera. And I'll do more of that with .NET 6. A few things I'd love to ask of people. If you're still on .NET Framework, I would highly encourage you to look at moving to .NET Core. It's where all the innovation is happening. It's where all the performance improvements are happening. And as I mentioned, while we still will support .NET Framework for a very, very, very long time, we're not really investing in it in terms of new functionality or performance. And so all the perf improvements we're talking about here and in those blog posts, you really only get them from being on .NET Core. On top of that, if you're already on .NET Core, that's awesome. But make sure you're staying current. We release a new version of .NET Core pretty much every year, and every one of those releases improves base functionality, improves base performance, adds new APIs that you can use to further improve your performance. And so staying current helps you to kind of ride the wave of all the latest and greatest performance improvements. The last thing I'd ask is a lot of these improvements are because of you, are because of folks like you that come and fix things that you find most relevant or that you're most interested in. We would love for you to get involved. That means submitting issues for things you think should be better, or even better, submitting PRs to just fix it for us. Work with us to make .NET the best that it can possibly be for you. And so with that, I'll say thank you, and I think we have some amount of time for Q&A, which I will be more than happy to take ad nauseum. So thank you very much.
Thank you so much. It was really cool. So as one would expect, we have some questions, and interestingly, they are all around how to make performance improvements to .NET. So it looks like people are excited about that. So just the basic one, how do I start to improve .NET performance? Where is the entry point? What is the process? How do I go about it?
Mm-hmm. That's a good question. So it depends on, I think, what you mean specifically. If you're talking about improving performance of your application that's using .NET, the first thing to do is to try and port your application. If you're on .NET Framework, get to .NET Core, which a lot of that is on updating your project file, dealing with any breaking changes that may have been introduced, and in particular, there is some functionality that we just haven't moved to .NET Core. Things like system.web doesn't really exist on Core, and so you may have to rewrite portions of the app that we're using those things. In .NET Core 2.0, we did try and bring back a huge amount of surface area. I think we brought back something like 20,000 APIs in .NET Core in support of people migrating, but there are still things that aren't available. There are tools to help with this. There's a portability tool that you can run, which will flag APIs that you're using in your .NET Framework app that may not be there or work the way you want them to in .NET Core. Yeah. We've also been shipping analyzers as part of the .NET SDK that help to flag functionality. For example, if you were looking to move to .NET Core because you want to run on Linux, it'll help to flag APIs that may not behave the same way or may not be implemented on Linux because they were sort of Windows-isms that had crept into .NET. So that's the first step. Get your app on .NET Core. Then after that is profile. Find the bottlenecks that are causing you to take a lot of time. You can use Visual Studio's profiler, which it's my preference. There are other tools that you can utilize, all the way down to things like PerfView, which is pretty low level. You can analyze for things like throughput. You can look for allocation, help you to find your bottlenecks. Sometimes the changes you'll make then will be in your own code to fix things where you could take advantage of either just fix problems in your own code or take advantage of new functionality that existed in .NET Core to make something better. For example, moving to spans, and just iterate fixing these issues. If you're talking about making changes to .NET itself, the very first thing to do would be to go and git clone https github.com/.net/runtime and get it building. In theory, it should be as easy as either build command or build sh, and probably providing some flags. There are full instructions in the .NET Runtime repo. I say in theory because you might have to install some prereqs that you didn't otherwise have. But you build the runtime, and then you can go in, and if there's a particular thing you want to improve, you make the change locally, you make sure it builds, you go up, you submit a PR to .NET Runtime, and we'll work with you then reviewing your pull request to try and get that change merged in. And then once it's merged, it'll show up in the next nightlies and the next previews and whatever the next release is we ship after that. If you have more specific questions about how to do that, please go to the .NET Runtime repo, and we'll be happy to work with you to do that. We love repeat contributors. We love new contributors. We love all contributors.
Actually, I have a question about that. I wonder
Sure.
how your team goes about having, well, I suppose there's tons of these pull requests. How do you not get overwhelmed by that? Because there's like 7 people on my team, and there's already too many pull requests.
So
How do you
sometimes
do
we
it?
do get overwhelmed, which is why there's about 200 pull requests that still haven't been handled in the .NET Runtime repo. It's usually the bigger ones that end up sitting for a lot longer because we have to spend a lot more time reviewing them. The small ones, they usually get merged within a day or two because we see it come in, we quickly review it, we validate it, and we merge it in. There are a few of us that spend a lot of our time reviewing PRs. I spend a lot of my time reviewing PRs, but it's important, right? It's how we move the platform forward. It's how we help everyone become a better developer from discussing the code changes that are being made and helping everyone to understand other options, things that may have been great, things that may have been not so great. And that helps to, in turn, make everyone a better developer, which in turn makes the technology that much better. So it's worth the time. But everyone on the team, on the .NET team, ends up spending some amount of time reviewing PRs. And then we encourage everyone else from the community to also review the PRs and provide their feedback and ask questions and help everyone can help everyone else move their support forward.
Yeah. So I was also wondering which percentage of these checks are automated. So obviously
Mm.
you have a lot of.
We have a lot of automated checks. We have about 4 million tests that run on any change on any PR that goes into .NET Runtime, and then there's about twice that run. So that's what we call the inner loop tests, and then we have a set of outer loop tests, which are the ones that don't run on every PR, but we run in rolling builds of several times a day to catch regressions that may have come in other functionality. So any given PR will be validated on, say, 10 different operating systems with these 4 million tests. And then we also will do style checks and things like that. We run analyzers as part of the build. We've turned on a good number of the built-in analyzers that are part of the .NET SDK. We've turned on some additional analyzers that are available through Visual Studio as a NuGet package.
Steven,
some additional
Steven,
yeah.
I'm sorry for the interruption, but the time is over. So
okay.
I want to invite you and all the people in the audience who want to ask some question about performance or .NET Core development to the discussion zone. And so you could continue your reply and the whole discussion.
Great. Thank you all, and I'll see you in a couple minutes, I guess.